Symmetry. I guess we should thank many people for making this possible, among them the ERC and the Center for Rationality, who has generously provided this room, and the Institute for Advanced Study tomorrow. And well, perhaps more than anybody else, Amit Solomon. And I don't think I have to explain. So
good.
And yeah, Yoel also. And so I guess with that in place, we should introduce our first speaker, Cedric Membrez from Tel Aviv. We'll be talking about the Fukaya category.
Thank you very much. Is this working?
Yeah,
it's only for the camera.
Oh, okay. I understand. Okay, so in this first talk, I'd like to present the Fukaya category as an A-infinity category. And so, generally speaking, a Fukaya category is an algebraic object that encodes information on the Lagrangian submanifolds of a symplectic manifold. And there are different versions of the Fukaya category. And in this talk, I'd like to present the possibly simplest case of the Fukaya category of an exact symplectic manifold. And if we have time near the end, I'd like to also introduce a second version called the Monotone Fukaya category. So let's start off with the setting. Here M is an exact symplectic manifold. And in this manifold, we look at d plus 1 Lagrangian submanifolds. We label them as follows. We have L0 until LD. And we want these Lagrangians to be exact and compact.
Did you put that in exact?
Exact, I'm coming to that. So exact means that if we restrict this primitive of the symplectic form to Li, then this is just an exact one form. So this is equal to the differential of a function fi, where fi is a function from Li to R. Okay? And now we make the assumption that Li intersects Li plus 1 transversely. Okay? So Li has a transversal intersection with Li plus 1.
Only Li plus 1, no LG.
No, we don't care about the other. Only this. Okay? And this holds for all I. And when I say for all I, this means modulo d plus 1. So LD intersects L0 transversely. Okay. And so now with this condition, we can now define the Floer complex. So this is defined to be CF of Li plus 1. So what you do is you pick your favorite field, call it K, and you look at the vector space generated by these intersection points of Li and Li plus 1. So I'll write this way. Okay. Okay. So we'll move on over here. So now we define composition maps. Okay. So in order to do this, we first have to pick an almost complex structure. So we pick a J in curly J of M. And so this curly J of M is a space of omega compatible almost complex structures. Okay. Great. And so now we pick a homotopy, a relative homotopy class beta. So this lies in pi 2. of M relative to the union of these Lagrangians, L0, LD. Okay. And so such a relative homotopy class has an index, which is given by the Maslov index of this disk. Okay. Great. And now we take D to be the closed unit disk in C. And yeah, okay. And so now for generators in the Floer complexes, so we pick a pi and CF of Li plus 1. And we also pick an element Q in CF of L0, LD. So for these, so here I goes from 0 to D minus 1. We now define a moduli space, which consists of the following elements. So M depends on these pi, so we have PD up until P1. Q, it also depends on this relative homotopy class, beta, and it depends on the almost complex structure J we chose. And this is given to be the space of, first of all, we take D plus 1 ordered points on the disk, D. On the boundary of D. Kind of running out of space here. We take maps that go from D without these ordered points into our symplectic manifold M. And now we have the following conditions on these maps, namely the anti-holomorphic part of the differential should be equal to 0. So du, the anti-holomorphic part, which is equal to du plus j composed with du composed with I, this should be equal to 0. I'm sorry, I'm running out of space here. And we want this map U to map the boundary of the disk to these Lagrangians. So U of delta di is contained in the Lagrangians Li. And furthermore, we want U to be asymptotic to these generators Pi and Q at these boundary points. Okay. So I'll write it this way. U goes to Pi, Q when Z goes to Zi. Okay. Oh yes, and we have one last condition, namely we want the.
Why don't you just extend it? Why didn't you find it?
So I'm trying to define this category in the I'm showing an example in the simplest case. And actually, in general, we won't take the generators to be intersection points. We'll take them to be Hamiltonian chords. Okay. So that's why we don't include these points. But actually, tomorrow we will. Yeah?
What is EI?
Okay, I'll draw a picture afterwards, but this is a boundary component between the point Zi and Zi plus 1. So with a picture, everything will actually be clear.
Pseudo-holomorphicity condition is only in the interior?
So yeah, it will result from this that U will be continuous up to the boundary. Okay. And so the last condition is that the map U represents the class beta. Okay. So this is the end of the set. Okay, so I promised you a picture that would resolve everything. And
Would you remind what's the Maslov index?
Oh, okay. So the Maslov index is as follows. A class beta is represented by a map of the disk. Actually, I'll just draw the picture and then I'll explain. Okay. So here we have our disk. Okay. U. And so on this disk, we have d plus 1 punctures. Z0, Z1, till Z D. Okay. The boundary components are here, d delta d1, delta d2, delta dd. Okay. And this map U, it maps this disk into the symplectic manifold M such that these boundary components lie on these Lagrangians. So here we have the following picture. So if we take this point here to be Q, this point here to be P1, then this Lagrangian here is L0, L1, this would be LD, PD, okay, and U represents beta. So what is this Maslov index? What you do is you pull back the symplectic vector bundle via this map U to the disk. Since the disk is contractible, you can find a trivialization of the symplectic vector bundle over the disk. And now you pull back the Lagrangian subbundles, given by the tangent bundles of Lagrangian, to the boundary of this disk. And so this gives you, at all points except at the punctures, Lagrangian subbundle of the symplectic vector bundle. And basically what this Maslov index does is it measures the twisting of this Lagrangian subbundle in this trivialization.
The question is, because you don't have symmetry
Yeah.
in this point.
Yeah. So what you do there is you can define, so for instance at this point, you look at the symplectic vector space corresponding to it, and there's a way of defining a canonical path between two Lagrangian subspaces. And so along this path you adjoin. Okay, very good. So that is, that's the Maslov index. Okay. Oh, I forgot something, I'm very sorry. So, I don't have enough space. So on this moduli space, you also have an action of a group, which is given by the group of holomorphic automorphisms of the disk. So this equivalence relation is given by the action of PGL to R, which is just the group of holomorphic automorphisms of D. Okay? And this group acts by reparametrization. So this means that, so for a pair consisting of Z0 up till Z and U, this is equivalent to phi of Z0, phi of ZD, and U composed with phi inverse. Okay? Where phi is an element of our group PGL2R. Okay. So I need some more space. How can I clean this blackboard?
I think there is. I think there is.
Oh, there we go. Thank you. So there was a question?
Please explain the first condition. You said, what does it mean?
This condition?
Yeah.
Just means that U is J holomorphic.
Oh, okay.
Okay.
Maybe I think the first equality is a definition.
Oh yeah, I mean this is
Condition to
it's definition. Definition, yeah. So you take the anti-holomorphic part with respect to this choice of almost complex structure. Okay.
So where is there a condition there?
Here?
Zero.
It's zero.
Zero.
Oh, sorry. I'm sorry, I ran out of space here, so it's. Yeah?
Why would you allow the automorphism to permute the boundary ones?
Yeah.
Why don't you fix it then as part of the data space?
I mean, so this group acts 3 transitively. So what you could do is you could fix 3 points and then let the others vary. But yeah,
Do you maybe want to say PSL2?
I want the group of holomorphic automorphisms of the disk.
No,
Is-
the question is, you want to disk to go in the center. Homological, we have to put this.
I have to put
We
PS.
have work if you have to do
Not a
PSL2.
big difference. It's-
Okay. There we go.
I think,
And then we'll preserve that order of the boundary point.
Ah, okay. Okay. So, okay, now I'm going to give you a general statement. This is standard in the literature. So, under genericity assumptions, so this means that we get transversality for this equation.
there is assumptions, it's assumptions on J.
On J, yeah, exactly. And further conditions, on the Li that I'm not going to specify at the moment, it follows that this moduli space, so M, PD, P1, Q, beta, J, this moduli space is a smooth orientable manifold of a certain dimension. So the dimension is given by the number of punctures, -1. So we have D minus 2. Oh, okay. D minus 2 plus the index of the class beta. Okay. And so now with this, we can now define the composition maps. Mhm. Is, excuse me? The okay. And so these composition maps, they are K-linear maps. And I denote them by mu d. And they map the Floer complexes of LD minus 1, LD tensor CF L0 L1 to CF L0 LD. And this is defined as follows. Mu d of PD up until P1 is defined to be the sum over all Q in CF L0 LD. And here we take classes beta such that the index of beta is equal to 2 minus d. Can everyone read this? And then we take the signed count of elements in the zero-dimensional moduli space, M, PD, P1, Q, beta, J, and multiply this with Q.
Multiply with Q. Yeah, okay. Now, of course, there is assumption here. How does its composition depends on J?
So one can show that this doesn't depend on J.
So it doesn't depend on J. after quasi-equivalence, doesn't depend on J and knows. What is this thing?
It doesn't depend on J at all. Wait.
I have a little word.
Yeah, I mean, this operation
Doesn't.
will depend on J.
Okay. Well.
But
Yeah.
the whole structure we
No, there's a difference to it.
Aha. You mean. So. Okay. Yeah. When we switch to the cohomology category, then it doesn't depend on J. But yeah, here of course it depends on J. But we get invariance of J when we look at. Okay.
It depends on J.
Yeah.
So two questions if I may. So first of all, the dimension of M, P, D, it doesn't depend on the dimension of M?
No.
Okay. And secondly, you didn't say that this space is compact. How do you count the number of elements?
So that's also a theorem given by Gromov compactness. And Gromov compactness states that you can, in general, compactify the space as a compact.
So you have to
Repeat the phrase. You can in general, just repeat the phrase.
You can, in general, the space can be compactified. Okay. And
Count the number of points.
exactly.
You have to compactify.
Yeah, this is the compactified case. In the case of zero dimension, it's compact. It's compact.
This space which you can see,
Mhm.
you count the number of points in this space, or not compactify.
On this space because it is compact. So in dimension 0, it's compact.
Okay.
And in higher dimensions, there is a compactification.
Okay.
Okay. Yeah. And was that? Okay. So I want to look at some examples of this map because these examples will show where the infinity structure comes from. Okay. So we look at the case where D is equal to 1. Okay. So here we have the map mu1 goes from the Floer complex of L0, L1 into the Floer complex of L0, L1. And so what this map does is it counts, it considers maps that go from the disk with two punctures, Z0, Z1. Then map this disk to a J-holomorphic strip. Such that the strip has boundary on L0 and L1. Okay. And so now we have the following statement, namely that mu1 composed with itself is equal to 0. And so the idea for the proof is as follows. So we considered the Gromov compactification of the one-dimensional moduli space. So I'll label this moduli space by M, P, R, beta, J for the index of beta equal to 2. So this condition implies that the moduli space is dimension 1. So now we can look at the boundary points of this compactification. And the Gromov compactness theorem says precisely that these boundary points can have three types, so to speak. Okay? So the boundary points can be broken strips. They can also be configurations with disk bubbles. I'll just write this like this, disk bubbles. Or these boundary points can be configurations containing sphere bubbles. So these disk bubbles, they correspond to J-holomorphic strips with a J-holomorphic disk attached to the boundary. Okay. And these sphere bubbles are also J-holomorphic strips with J-holomorphic spheres attached to an interior point. Okay. And so now with the exactness assumption, we can rule out these two cases of disk bubbles and sphere bubbles, because since our Lagrangians are exact, there can be no J-holomorphic disks with boundary on the Lagrangian. And since our symplectic manifold is exact, we can't have any J-holomorphic sphere in the symplectic manifold. Okay? So there exists no non-trivial J-holomorphic disks and spheres. Okay. And so now the only boundary points that we can have are these broken strips. So let me draw this. So the boundary points look as follows. R P prime. So here we have a broken strip such that P connects Q prime, and Q prime is connected to R. And we have another broken strip which has a different point in the middle, Q, L0. Okay. And so now we know that the boundary points are precisely of this form. And now with the help of a gluing theorem that states that all such configurations are precisely the boundary point of a one-dimensional moduli space, this shows, well, this gives us the claim. So. And so, yes, so this implies that the coefficient of R under mu1 composed with mu1 of itself, of P, is equal to 0. So, yeah. Claim. Yeah. Okay. Let's move back over here. Okay, so now, since mu1 is differential, yes?
Regarding the equation, when M is one-dimensional, can
M is one-dimensional.
in the modular space,
Oh, okay.
can it, in general, the non-exact space, can you have two kinds of topologies appearing on the boundary, or
What do you mean, two kinds of?
can you have a broken strip with a disk bubble, for example, in the boundary of the one-dimensional?
Oh, no, that would have too high codimension. And you can rule that out by transversality. Okay, so now we can make the following definition. So we define the Floer cohomology of L1 and L0 to be precisely the cohomology of this Floer complex with this differential mu1. Of L0 and L1. And so there's another statement which states the following. If L1 is Hamiltonianly isotopic to L0, then this Floer cohomology is isomorphic to the singular homology of L0. Is this clear what Hamiltonian isotopic means? Okay, so this means that, so for a given Hamiltonian function on the symplectic manifold, call it H, with the help of the symplectic form, one can define a Hamiltonian vector field associated to this function. And so this Hamiltonian vector field generates a flow, and this assumption is that L1 is the image of a time one map under this flow of L0.
Probably you have a couple of more statements here. One is homological dependent J.
This does not depend on J, yes.
The second is that if L are changed by Hamiltonian flow, homological change.
Excuse me, if L?
If you change L one by Hamiltonian flow,
Yeah.
then homological change.
Yeah. Okay, so let's see. The time is okay. So now I'd like to look maybe at another example of this composition map in the case where d is equal to 2. And so here, z0, z1, z2. And this is mapped into such a triangle. P1, P2, so 2. Okay. And so in this case, we have the following statement, namely that mu2 satisfies the Leibniz rule. No, on the chain level. So this means mu1 composed with mu2 of a point P2 and P1. This is equal to, and so now I'm going to be messy with the signs. Please forgive me. But in general, we have signs here depending on the degrees of these generators. But I don't want to go into too many details concerning these signs. So here, right, plus minus, mu2, mu1 of P2, comma P1, plus minus mu2 of P2, comma mu1, P1. Okay? So, okay. So once again, the idea of the proof is that we considered the Gromov compactification of a one-dimensional moduli space. So we take a moduli space M, P2, P1, Q, beta J. And here we have the index of beta equal to 1. Okay. And by the same arguments before, this Gromov compactification cannot contain any disk bubble configurations or sphere bubble configurations. It can only contain broken strips. And so this means that we get 3 possible boundary points of this one-dimensional moduli space. And they look as follows. Okay, so take this to be Q. This here is P2, P1, and here L2, L2, L1, 0, L0. Here we have P2, Q, P1, L0, 2, L2, No, wait a sec. Sorry. Q. Zero. So these are the three possible boundary points in this moduli, in the compactified moduli space. And so now one sees precisely that this configuration here corresponds to terms here on the left-hand side. It's precisely the composition of mu1 with mu2. These two terms here, well, this term here corresponds to precisely this term here in this equation. And these boundary points here correspond to the terms given by the last term in the equation. So, yeah. So once again, we have a gluing theorem that states that all such configurations can be glued, well, can be mapped to this one-dimensional moduli space. So all such broken strips are boundary points, and this implies the claim of the proposition. And so now, with this equation, let's call it star, we see that mu2, actually, it induces a multiplication on cohomology level. So, on cohomology level, we can look at the map, which is given by HF, L2, L1, tensor HF, L0, L1, and to HF, L0, L2. Okay? And so now I don't want to lose too much time, so I'll try to shorten the exposition. Okay. So maybe we have the following remark, that one can show that this mu2 is on chain level associative up to a homotopy given by the mu3 map. And this implies that this mu2 descends to an associative map on cohomology level. Okay. So mu2 associative to homotopy given by 3. And so this implies that the map on cohomology is associative. Okay. So, yeah, so actually, it's just one remark. Yep.
Why is mu3 vanishing from the homology?
Why is mu3 vanishing?
You said the homology is given by the mu3.
Yeah.
So you said it's associative with homology. So I understood it is implied that the mu3 vanishes.
No, the statement should be that non-associativity would be mu1 applied to mu3.
Yeah.
And this is why it vanishes. In this case.
So, yeah.
But this one should.
So, okay, yeah. I could write that.
Doesn't matter if you don't finish everything you wanted to say.
Okay.
Your original plan.
Sure. Okay. Okay, so yeah. So maybe another remark about this mu2 operation in cohomology. So we saw before that these Floer cohomology groups are isomorphic to the singular cohomology. And this operation mu2 corresponds precisely to the cup product on cohomology of L0. Okay. And so now I'd like to define the Donaldson Fukaya category. Okay. And so here we say the Donaldson Fukaya category, EFM. This is a k-linear category. And the objects, in this case, are exact compact Lagrangians. The morphisms are given as follows. This is precisely given by the Floer cohomology groups of L0 and L1 for all objects L0. Okay. And the composition of morphisms this is given by this mu2 operation. Okay. Yes, and maybe one last remark. There's also identity morphisms, which is given by, well, this isomorphism here from the singular cohomology to these Floer cohomology groups. So EL. Okay. Yeah.
What happens when the Lagrangians are transversal?
Yes. So then you just basically need more technology to get the same thing. Yeah. So this is exactly, well, this is the case where you start looking at perturbations of your holomorphic strips. So if you take L0 and L1 to be the same Lagrangian, you choose perturbation data, which consists of, first of all, a choice of Hamiltonian, such that the Hamiltonian flow gives you a transversal intersection between L with the image of L under the Hamiltonian flow. And instead of intersection points, you start looking at Hamiltonian chords between these two Lagrangians. Okay. So, yeah.
So, could you do it simpler? If you say Lagrangian, moving the Hamiltonian flow is actually become transversal, and then take intersection.
Yeah, but the problem is that you want to define all these composition maps, and these composition maps have to satisfy a bunch of associativity equations. And so you have to choose compatible Hamiltonians, so to speak, for all these different combinations of Lagrangians. And so this basically...
Let me try to understand.
Oh, for the Donaldson Fukaya. Yeah.
Is it true that if you take two Lagrangians, and you calculate one obtained from the other, the Hamiltonian flow, then corresponding objects are isomorphic?
Yes.
Then
Yeah. Okay. So, yeah.
Homology level.
no, as
Come on.
objects, in the categories is only cohomology.
In this,
No,
in
no,
this particular
I'm talking about this.
Okay.
Then they're just, then there's no problem in choosing. Representing the just transversal.
So the problem shows up when you look at the Fukaya category, and that's okay. Okay, so we'll get there. So maybe one remark about the Donaldson Fukaya category is that so these higher order composition maps, mu d, when d is greater than or equal to 3, these are basically lost in this category. And so what we want to do is we want to retain this information, and this leads us to the Fukaya category. Yes? Yeah, mu3, but what about mu4 and higher mass products? Yeah, okay. Okay. So let me write down the definition of an A-infinity category. Okay. So here we also have a set of objects. Okay. And morphism spaces are graded vector spaces. For 0. Okay. And we have composition maps. For d greater than or equal to 1. I'll write it down like this. Mu d goes from maps into Hom A of x0, xt. And note that actually these maps, they shift the degree, 2 minus d. Okay. So this just means that the degree of the vector space is shifted down by 2 minus d. Okay. And now, most importantly, they have to satisfy the so-called A-infinity associativity equations. So that satisfy So these A-infinity equations, I'll write them over here. Okay. So here 0 is equal to sum of m equals 1 to d. Sum of n equals 0 to d minus m. And then we have a sign, which I'm not going to specify, of mu d minus 1 plus m plus 1 a. ad up until an plus m minus 1. And now we compose it with the mth composition maps. I'm running out of space again. Terrible. an plus m up until an. That's 1. Please excuse my writing. This is not really, it's not really clear what I'm writing here. So the composition map of degree d minus m plus 1 is composed with the composition map of degree m, and we take the sum over all such choices of m, okay? And the total sum has to equal 0. This is the A-infinity associativity equation. Okay? Star is a sign. So actually, so star is equal to the degree of A1 plus the degree of A n, there we go, minus n, yeah, okay. Okay. And so now we can write down the Fukaya category. Okay, so once again, we have an exact symplectic manifold. And so Fukaya category of M, Fm, is a K-linear A-infinity category. And here the objects are, as I described before, Lagrangians. And so on these
Or exact Lagrange.
exact Lagrangians. So they have to satisfy, they have to be exact, compact. Choice of orientation. And since we want these moduli spaces of disks to be oriented, this means, well, we can assume that these Lagrangians have a, or we want that these Lagrangians to have a spin structure. Spin. And if we want a grading on these morphism spaces, then we need these Lagrangians to have vanishing Maslov class, and we also have to make a choice of grading. So yeah, L equals 0, and grading. Okay. And now the morphism spaces are precisely the Floer complexes.
Now, you define these spaces when there is 0 and 1 were transverse.
Yeah.
What are we doing here?
Now I'm cheating.
So,
I'm cheating.
more cheating.
So, okay, in general, one would have to choose perturbation data.
Let's
That was,
just move.
okay. Now I'm cheating. Okay.
Let's move.
Or we can also just look at a finite.
I don't know whether you need the perturbation data.
Okay.
If you change J, it's still not transverse.
If you change J,
Yeah, it doesn't happen.
L0 and L1 won't become transverse once you change J.
true. But if you
What-
choose,
what-
so for two, assume we take the same Lagrangian L. L0 and L1 is equal to L. You choose a Hamiltonian function,
Okay, move.
okay? L. Choose a Hamiltonian function such that the image is transverse.
Okay.
Phi 1 H of L. Okay? And so the Floer complexes are given, well, by the intersection points of this L with its image of phi 1 H of L. But actually, we define the Floer complexes to be the Hamiltonian chords that start on L and land on L. Okay. Okay, so we take gamma from 0, 1 to M such that gamma dot is equal to xh opposed with gamma. Okay? This is a Hamiltonian chord. We want this Hamiltonian chord to start on L and land on L. Okay? And then we look at perturbed J-holomorphic strips that connect one Hamiltonian chord to another Hamiltonian chord, or that connect, well, that map this disk with punctures on the boundary.
So the Hamiltonian chords are now a substitution of intersection.
Exactly, yeah.
Is it the same number?
It is the same number.
Or just
Okay. And so the idea now is to pick for any pair of Lagrangians suitable perturbation data, namely this choice of Hamiltonian, H. And also, since you want transversality of these moduli spaces, you want a choice of family of almost complex structures, so that these moduli spaces become transverse and we get a manifold. Okay?
the same way as before. Now you have this home, what it is. Does it depend on choices?
It does depend on the choices, yeah. Okay. But one can show that if we make different choices for all the objects, then we get equivalent categories. Okay. Okay. So, yeah. So now we have composition maps. okay, which are precisely these maps from before, mu d, Cf star, LD minus 1, LD tensor, Cf star, L0, L1, Cf star, L0, LD. And now we have to show that these composition maps satisfy these A infinity associativity equations. And this is precisely due to the fact by considering the Gromov compactification of these one-dimensional moduli spaces. So maybe I'll just write Gromov compactification implies A infinity equations. Okay. Great. Okay. So this is basically the definition of the Fukaya category in the, I don't know, in possibly the simplest case. And so now I'd like to say something about the monotone Fukaya category. I don't have much time left, but I hope I can at least explain what happens in some short words. Okay. Okay. So here we don't have a exact symplectic manifold. We take M omega to be a monotone symplectic manifold. So this means that the cohomology class of omega is positively proportional to the first Chern class. So it's equal to 2 tau C1, where tau is a positive constant. And now in this category, the objects will be monotone Lagrangians. Okay. So we take L in M. We want it to be a Lagrangian that satisfies the following conditions. Well, first of all, we want that the fundamental group of L maps, well, this maps into M, and we want this map here to be trivial. The second condition that we impose on these Lagrangians is the monotonicity condition. So monotonicity is given as follows. So if omega, this is in symplectic form, it defines a map from H2, M relative L into R. Then there's another map called the Maslov index, like what I explained before. It goes from H2, ML into Z. And a Lagrangian is monotone if these two maps here are positively proportional. So we want omega to be equal to tau mu, where tau is precisely this constant from before, from the monotonicity condition on the symplectic manifold. Okay. And so here we have, well, some further conditions. Namely, we want L to be oriented. And since we want an orientation on the moduli spaces, we also want L to be spin.
I don't understand how you map H2ML to R. H2M, of course, map to R, you just integrate formula class. But if you have n on Lagrange, and you don't put any condition on Lagrange,
So actually,
exact nothing, why is map well defined?
so the condition that the condition that it is Lagrangian defines gives you a well-defined map from. Okay. So now note that everything that I said before doesn't quite go through to the setting. because in general, monotone Lagrangians, they can have pseudo-holomorphic disks on them. Okay. So monotone Lagrangians bound J-holomorphic disks. So in particular, all these arguments with the Gromov compactification, these boundary points can contain, well, configurations with disk bubbles. Well, maybe an example of a monotone Lagrangian with the J-holomorphic disk on it is just simply when you take S2 and you take L to be the equator. L, S2. Okay. And so if L splits S2 into 2 halves of equal size, then this L is monotone. Yep. Okay. So now let me also state another fact, that namely if L is oriented, then the minimal Maslov index, which is just given as the generator of the image, well, the positive generator of the image of mu, then this is greater than or equal to 2. Okay. So this is the minimal Maslov index. Okay, so now we pick an almost complex structure that's compatible with omega, and we pick a class beta in pi to ml, such that mu of beta is equal to 2. So if the minimal Maslov index is greater than 2, then this is just void. Okay. Okay, so now let me write down the following statement. So when we consider the moduli space, which I call M beta J, this is defined to be the space of all J-holomorphic disks with boundary on L that represent the class beta. And I also want them to have one marked point. So J-holomorphic disks on L with one marked point. Okay. So under this genericity assumption for the almost complex structure, this moduli space is a smooth, oriented, compact manifold of dimension L. Dimension equal to n. Oh, sorry. N is the dimension of the Lagrangian. So yeah, we get smoothness by this transversality assumption. The space is oriented due to this assumption that
L appears in the left side requirement that what is, I don't see, M beta J.
J-holomorphic disks on L
Okay.
with one marked point. And yeah, so we get oriented spaces by assuming that L is spin. And so now the most important point is that this is a compact manifold of dimension n. And how do we see that this is a compact manifold? So once again, we can look at the Gromov compactification of the space. And since now this Gromov compactification can contain configurations with disk bubbles, we can analyze the situation. But note that we have the condition that the minimal Maslov number of beta is minimal. And so in the case of a disk bubble, this would actually give us 2 disks. And the Maslov indices of these 2 disks would sum up to the Maslov index of the original disk. And since this Maslov index is minimal, this can happen. So we can rule out the case of disk bubbles.
Is Maslov index always positive?
No.
So why can't you have
But
minus n minus 10?
so by transversality,
And 6
yeah.
disk to come up.
So by transversality, you can't have any J-holomorphic disks with negative Maslov index. Oh yeah, true. Yeah, that also. Yeah, by monotonicity, since J alomorphic disk always has positive symplectic error, then it doesn't work. Okay. Also, maybe a picture. This is our disk, and we go towards the boundary. Then we will get such a configuration. So mu1 and mu2 should be equal to 2, but since since 2 is minimal, we can't get any splitting in this way. Okay. So now, I'm really sorry. Huh?
Is there going to be a stopping point soon?
Yeah. In 5 minutes. Can I get 5 more minutes? Or do you want me?
Maybe better if you do your next lecture.
I can also make it in whatever you want. I mean, I'm sorry, it's kind of a bad point to stop. Maybe 2 more minutes?
Okay, 2 minutes.
Okay, I'll make it quick. Okay. So, we have a map called the evaluation map. Maps mu beta j into L. Okay? And we call mu beta the degree of this map. And so now we define a number, double of L. It's defined to be the sum over all beta of nu beta. This is a number in Z. It's finite. Okay. Okay. And so now the problem in this setting of two monotone Lagrangians is as follows. So if we take L0 and L1 monotone, and L0 intersects L1 transversely, then we can, again, as before, try to define this differential mu1. Okay? But in this case, where we have, in this monotone setting, it turns out that mu1 composed with mu1 applied to an element x isn't always equal to 0. It's equal to omega L0 minus omega L1 times x. Okay. So if we have a moduli space, a one-dimensional moduli space of strips connecting x with itself, then what can happen is that the boundary points can precisely contain such disk bubbles, because the strip degenerates to a constant strip, and we get a bubble on each of the Lagrangians, or we can get a bubble on the Lagrangians. And so now in the case where we take two Lagrangians such that these numbers are equal, we get a well-defined differential, and one can define Floer cohomology for monotone Lagrangians, and one can extend this notion of a Fukaya category to the case, where we have objects that have equal number, omega L. Okay. So, yeah, maybe let me just write that down. For W in Z, or sometimes we count this number in C, we get Fm W is a Fukaya category. Is the Fukaya category, which consists of the same composition maps as before, but here we just restrict the Lagrangians we look at to be precisely those that have the same number of J-alomorphic disks through a generic point. I'm sorry, I kind of had to rush at the end. I'm sorry about that, but yeah.